I was going to record this chapter at my lab with Monty, but unfortunately, circumstances kind of changed, so you get to see part of my living room. Anyway, so I apologize for this, but my son, I dropped him off at school, and then instantly I got a call from the nurse going, "Your son's sick," which was quite a 180 because he ate all his breakfast and he seemed perfectly fine this morning, but if you have kids, you know how it is. So here we are, and I didn't want you to wait, so let's go ahead and dive into chapter 2, which I like to call Biochemistry or Electron Boogaloo, because what we're going to be talking about is pretty much how electrons drive pretty much everything in chemistry, and because chemistry drives biology, why that's important. So, now remember, I mentioned this last night, and I'd like to mention it again in the fact that, there we go, that science is actually kind of like a pyramid. Now, when you get to the top, it kind of gets a little all over the place. But if you're looking at everything, we've got fields arranged by purity, or if we look at it like I said last night, it's a pyramid. Everything, everything is based on math. That is the language of the universe. Pretty much if aliens came tomorrow, that would be probably the first way we'd try to communicate with them, is through math, because numbers are kind of universal. Now, how they count, we have 10 fingers, so therefore we've always based our math on base 10. Forgive my giggles, my son giggling in the back. Anyway, aliens could have a base 3 or something, but we could still figure it out. So math is the basis of all of science. And then we go, math explains physics, because it uses, if you ever take a physics course, which actually are a lot of fun, because physics can be a little non-intuitive in spots that you wouldn't think. It's actually kind of cool how you look at things in physics. Of course, I'm such a nerd. I kind of enjoy it. But anyway, me and calculus, though, we don't get along. So, oh well. So anyway, physics, to explain the laws of the universe, how the universe works, we're always arguing that, but a lot of the time you have theoretical physicists, and then you have the mathematical physicists, and those are the ones that are usually taking what the theoretical physicists are saying, and then try to make sense of it using math. That was the interesting thing that Einstein gave rise to, is before Einstein, people used to get really poo-pooey on theoretical physicists. They'd sit there and say, well, the math doesn't support it. And so they'd look down on the other half of physicists. So it was kind of an interesting hot mess. Look up Einstein's life, although he was a bit of a not so hot to his wife. But anyway, so physics explains chemistry, and basically that's where we're going to start today. We're going to start right here because chemistry explains biology. And we need a little bit of chemistry before we can move into how everything works on a cellular level. Because we need to know why all these molecules are getting together in the first place. It isn't just brotherly love, or sisterly love, or whateverly love. It isn't love. It's electrons, and we'll get into that in a minute. So, remember, all matter is made up of atoms, as hence my terrible joke from last night. Can't trust an atom, because they make up everything. Anyway, I have plenty more bad jokes for this course. So many bad jokes. All the dad jokes. And if you have some, send me more. I like telling them, if you can't tell. Anyway, so these basically an atom is a unit of matter that cannot be broken down by chemical means. In other words, at one point, there's got to be a place where, if you take a stone and you cut it and you cut it and you cut it and you cut it, there's got to be a spot where you can cut no more. And that is the theoretical atom. That's where the original ancient Greek hypothesis of an atom came from. However, yes, then you can sit there and go, well, what about those big machines that you just throw two atoms and smash them together? Yeah, well, the ancient Greeks didn't have those. So we do now, and we smash them all the time, and that's actually how we make some of the more crazier elements towards the end of the periodic table. But anyway, we'll talk about that later. So anyway, there's 3 parts basically that make up an atom. The electrons, which are negative, the protons, which are positive, and the neutrons, which are neutral. Both the neutrons and the protons make up the nucleus. And I have a wonderful video, I hope I linked it, that shows, if you want your mind blown, highly recommend watching. It's another TED Ed. He describes how big is an atom, because what you see in textbooks and some of the diagrams I'm going to show you here are not what they look like. And the only reason we draw them that way is it's the best way we can kind of represent them. Like this picture right here with the orbits that you're looking at and everything like that, that's not technically what they look like. And that's gone through a whole history. I just unfortunately don't have time to get into. It's a really fascinating story. Still, fun stuff. But anyway, so the neutrons and the protons make up the nucleus, which is in the middle part of the atom. Now, interestingly enough, they're orbited by the electrons, these negatively charged particles. And a lot of why atoms even bond in the first place is because of these electrons, and we'll get into that in a moment. So keep in mind, it's the electrons that are the reason why things bond together. So keep that in mind for a moment. Now, if the nucleus in the middle gets too large, it becomes unstable, and that's where we get radioactivity. Now, not all radioactivity is bad. We actually use radioactivity for good things, especially in biology. And we'll talk more about it later, especially when we talk about DNA and whatnot, because that's actually how we tag things with low-level radioactivity, because it actually fluoresces when we take pictures of it, so we can see individual chromosomes in the DNA. So it's actually pretty cool in that fact. So we actually do use radioactive isotopes on occasion to help us with understanding the smallest of the small in the cellular level world. However, too much radioactivity is bad. And like I said, I'll probably break into a couple of those stories going forth. Now, the periodic table. Like I was saying last night, I'm not a big proponent of making people memorize things. I like to make you use things until you've pretty much memorized it through using it. Because if you know how to use a thing, then you can move on and go, wait, I know how to look this up and use this. Because we have mini computers in our hands for a reason. The world's knowledge is at our fingertips, and that's a good thing, although it can also be a bad thing when people are putting out cheeseburgers on the internet and saying it's the next greatest thing to cure cancer, which is, yeah, you know what I'm talking about, hopefully. Anyway, so the atomic number, so if you look at the, and hopefully this triggers something back from your school days, if you're looking at, of course, isn't this one of your school days? Moving on. Sorry, I've got that kind of a brain. Anyway, so if you look at the square, any one of these squares, at the top you'll see a number. Like, for instance, this is argon right here. That number is your atomic number, and it tells you 2 things that are really important. The number of electrons in that atom and the number of protons in the nucleus of that atom. For the most part, if you're finding elements in their natural state, which is hard sometimes, most of these guys don't want to stay in their natural state, and we'll get into that later. But this is looking at it if they were perfectly perfect atoms. So imagine these guys are being perfectly perfect for us for a day. So an atom of argon has 18 electrons and 18 protons. The positives and the negatives in a natural, normal, actually not natural, but a stable atom should equal. Okay, this is going to come back for bonding a little bit later. So electrons, the negatives, and the protons, the positives, should be equal in a perfect world. And in the middle is the atomic symbol or name, and this is argon. Now you may be wondering, why are some of these, these symbols off from the name? Like, for instance, iron is Fe. Why isn't it I? Well, that's because iodine got I before iron did. And the reason is a lot of these, if they don't have ones that match, it's usually because we're using their Latin. For instance, Fe comes from the word ferrous, which is Latin for iron. So if you ever wondered why Fe is iron, but you're like, where did Fe come from? It comes from ferrous. And you'll see that in several other places too. Like potassium, he's going to be somebody we're going to be talking about a lot as an ion. Potassium, he's K. So yeah, that might throw you a bit, but you're going to see him a lot in this course. You're going to see sodium a lot in this course. Oh boy, are you going to see him a lot. Carbon's our backbone of everything. We'll get into him in a minute. Actually, these three right here, carbon, nitrogen, oxygen, and then hydrogen right here are the four biggies. We'll get into them in a minute. But yeah, if it's the symbol name is off from its name, that's because it's usually we're using the Latin. Anyway, all right. And then at the bottom, you'll have another number, and that's called the atomic mass units. So what you do to use the mass units, and yes, all atoms have mass. It's just not a lot. And chemistry was really concerned with the mass of atoms because that plays into a whole bunch of math when you're balancing equations and all that fun jazz. You learn about moles and stuff, but we don't go into it in this course. But right here, that atomic mass at the bottom, usually you round up to the nearest whole number. So like you see 39.95. For our purposes, always round up to a whole number so that we turn that into 40. Now, to find the neutrons, you may be going, hey, didn't you say there's three parts, the electrons, the protons, and the neutrons? Yes, I did. To find the number of neutrons, which is usually different, unless it's in the upper elements, they're very much all the same, but in the heavier elements, the further down you go, they have more neutrons. That is this. You take the atomic number and the mass number, and you subtract them. So 40 minus 18, because I can't do stuff in my head. Because I'm a genius. By a genius, I mean, not really. So you're probably already yelling the answer at me, which is completely fine. So 40 minus 18 is 22. So therefore, argon has 22 neutrons. Pretty cool, huh? All right, moving on. So the main players, the elements we actually care about, because we're going to be talking about them a lot. Basically, we've got the four biggies. These are part of the bulk elements. The four biggies make up pretty much everything we're going to be talking about from here on in on a very level. Carbon is our friend. Carbon has the ability to bond with himself in like so many different ways, which is why he's the backbone of pretty much every molecule that makes up living creatures on this planet. And you may be going, well, isn't there other planets where there could be another thing? Yeah, we're thinking silicon because it can do the similar thing, but carbon is smaller, easier, and everybody loves carbon. So, especially if you're a biochemist. You are always talking about carbon. Anyway, so these are the big four. We're going to talk about them in a minute when we talk about the big four macromolecules. So there's four big elements that make up the four big macromolecules. We'll get to them in a minute. Anyway, then you've got the other guys that are going to pop in, and we're going to talk about these ad nauseum. Sulfur, calcium is a big one. We're going to be talking about him a lot. Phosphorus, definitely. Potassium's huge. Sodium as well. The potassium and sodium, pretty much the dance back and forth between these two elements drive your nervous system. So, party on. Nervous system. Anyway. So, trust me, we're going to be talking about him a lot. We're going to be talking about phosphorus a ton. And we're definitely going to be talking about potassium and sodium a lot. Now, there's also the trace elements. These are found in proteins and enzymes. We don't talk about them as much, which you might find weird because you'll notice halfway or, partway down here, iron's one of them. And you're like, well, isn't iron a major component of our blood? Yeah, but it's weird. We don't talk about him too much. We just talk about his ability in heme to grab oxygen. It's an interesting mechanic, and we'll get into that not this semester, but you'll see it more next semester in 169. So, cobalt, copper, fluorine, iodine. Iodine does pop up. We'll talk about him. Iron, manganese, and zinc. Now, there's also known ultra trace elements. These are poisonous in very, very large amounts, but we use them very sparingly, usually and to make certain hormones and whatnot, and that is arsenic. So yeah, we actually need arsenic in our body. However, we only need a very, very tiny amount. If we had any more, it would probably, kill us. So a little bit is just fine, but too much, not good. So anyway, so let's talk about bonding. So let's first define a couple of things, because they're not the same thing, although some people use them a bit, these words interchangeably. And remember, in science, we're very, very particular about our definitions, especially in medical biology. So we get very, very futzy about our definitions. So one of them is compounds versus molecules. Now, compounds are pretty much a substance made of joined atoms or two or more different elements. So like water, which is H2O, or sodium, or table salt. Now, when I say sodium in this class, you should be hopefully thinking sodium ion Na. But I'm talking table salt right now, and that's NaCl, which is sodium chloride. Boop. Which is weird because table salt is, table salt. And the two elements that make up table salt, sodium, if you throw it is a metal, and if you throw it in water, it explodes. And that's elemental sodium, not the sodium ion that's running around in our bodies. Thank you. And chlorine is in a natural gas form and can destroy your lungs. But if you put them together, they turn into table salt. So the magic of chemistry. When you put things together, it suddenly turns into something else. That's why my minor was in chemistry, because it's also very fascinating to me. Anyway, so molecules are groups of atoms held together by covalent bonds. And there's actually 4 types of bonds. There could be more, but I didn't get that deep into physics to let you know that. And one of them we don't care about, because we're not talking about that in this course at all. So there's going to be 3 we're going to talk about that are actually important. Now, covalent bonds is one of the most important of the 3 that we're going to be talking about. So molecules that are held together by covalent bonds can also be considered a compound. For instance, the 2 examples I gave you, water and table salt. Water is both a compound because it's H2O, but it's also a molecule because it's held together by a covalent bond. And we'll talk about that, how that works in a minute. But table salt, on the other hand, is not held together by a covalent bond. It's held together by a different type of bond called an ionic bond. Therefore, he's just a compound. He's not a molecule. So molecule is covalent bonds only. Compounds are just any type of bond, including covalent bonds. So water is both a molecule and a compound, whereas table salt is just a compound. I hope that makes sense. So let's go ahead and talk about these bonds. Why do atoms bond? And I mentioned earlier it has something to do with electrons. And that is this. All atoms, like I said, the pictures we have on 2-dimensional paper or on the computer or whatnot don't exactly show how these electrons move accurately. They actually are all over the place. They're just like, kids on way too much energy. So they're all over the place. However, we have discovered that they actually jump into different orbits, kind of like moons going around the planet, except a little crazier. Thankfully, planets are a lot easier to figure out than atoms. So anyway, so we've discovered that more often than not, mathematically, they'll hang out in certain orbits. Now, the orbits are not like moons around a planet, like on these pictures right here. We just draw it this way because it makes a whole lot more sense to our head, so we can think about it. Because the orbitals, and they do have names, like the s orbital is just a round orbital. The p orbital goes in a figure 8 shape. But keep in mind, this is a 3-dimensional figure 8 shape, so it's, yeah. The d orbital is like one of those crazy flowers. It's like, figure 8 on multiplied. And then we start getting into like the f orbital, which is like, and then even crazier. If you want to look up orbital models on the internet, it will blow your mind, because our brains usually can't handle the 3-dimensional insanity these orbitals represent. So that's why we draw them as circles. It's a little easier. So reality, Circles, so much easier to comprehend. See where I'm getting at? Anyway, now, these orbitals fill up. They have room for only so many electrons. Okay? So the innermost orbital is always 2. It usually always holds 2. That's what you actually see in a lot of parts of the periodic table, which I'm going to get into in a minute. But the outer orbitals can hold up to 8 or 16, depending on what. Now, that's called the 2-8-8 rule. So the inner orbital is 2, then 8, then 8, then 16. And you may be going, so what? The reason is the outermost orbital. That's where all the action happens. And a lot of these elements that you see in the periodic table, their outer orbital is incomplete, and they hate that. They want to have matching numbers of electrons in a full orbital. And if they don't get it, they are not happy. They are not happy at all. And they start doing strange things to get that full number of electrons in that outermost orbital. And they do that by bonding together. So that way they can trick themselves or steal from each other electrons to get that full orbital on the outside. So those are called valence electrons. So that brings us to the 2-8-8 or octet rule, which is what I was saying. All these ones want, with the exception of one group, and we'll talk about him in a minute, all of these guys are doing anything they can to try and exchange electrons until their outer orbital is full. And that sharing or exchanging of electron is what drives bonding of atoms. And those electrons have a very special name. They're called valence electrons. So those are the ones they're willing to trade or share or do whatever to get to that happy number, which is usually 8. 8 is usually their happy number. Hydrogen's one of the only ones that likes 2. He sticks at 2. 2 is his happy number. But everybody else, their happy, stable number is 8. So that's why it's called the 2-8-8 or octet rule, because 8 is their happy place. Now, speaking of noble gases, on the other hand, right here, the reason these guys aren't reactive, thank goodness, is because they're full. They have a full complement of valence electrons on their outer orbital. And that makes them super happy and super chill. That's why we use the noble gases like neon, helium, and whatnot. And we can put electricity through them and they go, it tickles. And the worst they do is glow, which is why we use them in incandescent light bulbs and whatnot. So, wait, is it the incandescent or is it the... Am I getting... No, the halogen. Yeah, the halogen light bulbs. Yeah, the halogen light bulbs. Not the incandescent. Now I'm thinking... Oh! Anyway, sorry. I'll have to think about that later. But anyway, the new ones that are curly, and then we're replacing with the ones with the, the tungsten bit in the middle. The Edison light bulb versus the Tesla light bulb, which is a whole story I could get into, but, don't have time for that, sorry. But if you want me to, let me know. Anyway, so these guys are super chill because they've got a full component, so they don't react. They're just like, sup, man? Yeah, I think everybody should just chill out. Now, the opposite holds on the opposite end here. The alkali metals and the alkaline earth metals are psychos because these guys only have 1, and these guys have 2. That's what these numbers way at the top of the periodic table actually mean. So everybody, 1A in this row right here, they have 1 valence electron, and they hate it. They hate it. And they're going to do anything they can to get rid of that 1, because it's easier than them trying to find 7. So they're going to be like, take it! Take my electron, please! Take it, take it, take it, take it, take it. So they're going to find somebody to try and pawn that thing off so they can go to their inner orbital, which is full. So they can feel full. So these guys are looking to give away. And they got a special name because of that. So again, 2A up here, same thing. 2A has 2 in their outer, and they're not as reactive as the alkali, but they're still pretty reactive. Now, the transition metals play by their own games, and we're not going to talk about them in this course because we're not going to talk about them in this course. Over here, if you see again, you'll see sometimes on a periodic table, you see it says 3A or it says 13A, 14A, 15A. Drop the 1 and just be 3. These guys all have 3 outer electrons. These guys all have 4. These guys all have 5. These guys have 6. These guys have 7. And notice, these guys have 1. Well, these guys love each other. They love to bond with each other. We'll get into that in a minute. Because they've all got 1, and these guys are all looking for the 7. The halogens are all looking for 1 more, going, please, we just need 1 more and we'll be complete, please. And the alkali metals are like, take my 1, take it, please. And that's how ionic bonding works. Noble gases don't bond with anybody because they're too chill for that. They already have 8. What do they care? So to get that 8, like I said, these guys do every wacky thing impossible, which is, or it's not impossible, it's actually happening right now. And here at the bottom are the radioactive buds. They aren't so much into bonding because they're too busy being radioactive, and that's, again, a whole nother course. Wish I could go into it. Now, he does a really good, this is my friend, Mr. Anderson. Again, he does a really good job of breaking all this down. So hopefully, if you found my explanation like mud, I would highly recommend watching his. He explains it really well, or you just want to, like, you know, get it in your head perfectly. Highly recommend Bozeman Science, or Mr. Anderson right here, my knockoff Brad Pitt, for a good explanation on how this works and how you read the periodic table. Because the periodic table is literally arranged according to how they bond, as well as the levels of electrons they have. The Russian scientist who actually came up with the periodic table and why it looks the way it looks, Dmitriev, was freaking genius. Honest to God. The more I use the periodic table, the more I sit back and go, God, that man was dang smart. Anyway, smarter than me. So anyway, let's get to bonding. Enough about that. So remember, all atoms want to be happy or stable, and to do that, they need that 8 valence electrons. Except for hydrogen, he just wants another one. He's just like, dude, I'll settle for 2. Just give me 1 more. So that's where the bonding comes in. So the strongest and the most important to biology is our friend, the covalent bond. He is the strongest of the bonding types because he shares electrons, and it's what happens is both atoms basically think that the electrons they're sharing are theirs, and therefore they don't break up because they're like, no, I can't leave without my electron, and the other atom is like, yeah, I can't leave without my electron. It takes a lot of effort to break a covalent bond. That's how powerful they are, and that's why we don't melt in the rain, which is a good thing when we all want to take a shower or take a bath. You know what I mean? So we don't dissolve in water. Given enough time, we do, but that's because water's persistent. We'll get into that, I think, in the next half of this chapter. Anyway, so as you can see right here, hydrogen likes to bond with itself because then they both have 2, so H2. And you can notice that it shares, so both of them think they have 2, so they're not going to split up. Oxygen will do the same thing. He both has 6, yeah, he has 6, right? Hold on, double checking. Yeah, oxygen's in lane 16. He's got 6. So anyway, sorry about that. I don't know why I was doubting my tiny little mind, but it happens. And then it's always good to double check. Always double check. And water is the same way. He's held together by covalent bonds because he's got 6, but then he gets 1 here, 1 here. That bumps him up to 8, so he thinks he's got 8. Hydrogen, grabs 1 from oxygen. He thinks he's got 2. He thinks he's got 2 H2O, which is insanely hard to break down. Breaking water down into hydrogen and oxygen does usually involve an explosion. And putting them back together also can involve energy, which you can see if you watch the movie The Martian when he's trying to make water for his potato plants. That's actually kind of true. Taking gas oxygen and gas hydrogen and using electricity to zap them into coming together. Yeah, it doesn't always work out. Anyway, so water's fascinating and insanely important. We'll talk more about him later and why water is... There's a reason why we're 70-some% water. Very good reason. And one of the reasons is he's covalently bonded. But anyway, there's 2 polar flavors of this, polar and non-polar, and I don't mean like the fancy water. And we'll get into that later, but basically some of these are completely even in how they distribute their electrons around each other, like the hydrogen H2 right here It goes in a nice figure 8 pattern on paper. And therefore it's even, so he's nonpolar. However, water down here, actually the electrons spend more time going around oxygen, which is actually way bigger than this image should show. So they spend a lot of time going around the oxygen. It slows them down a bit, and then they loop real fast around the hydrogens and then go around the oxygen again because he's huge. And because of that, the electrons spend more time up here than they do down here with the hydrogens. So therefore, this end of water becomes negative, and this end becomes positive. And because of that, water is like a whole bunch of little magnets, which allows it to freeze in a special way that other things don't freeze that way. And this is actually why water floats. So that's why ice cubes float. And I'm sorry, Titanic, that's why iceberg was there, and yeah. And then song, introduce song, and all sorts of stories and stuff like that. Anyway, moving on. So, now, remember when I said they get special names if they're giving or taking electrons? Well, here they are. This is where ionic bonding. So this is instead of sharing, so remember, covalent bonds share. Ionic bonds give and take. So ionic bonds is basically, like I was talking about earlier with sodium, he's got the 1 on the outside. He's like, please take it, please take it, please take it. And he's crazy enough to do it. And chlorine, who's go, I just need one more. I just need one more. And literally what happens is sodium hands chlorine his extra electron. However, this changes their charge. So when they have the number that you see on the periodic table, they are neutral. But because he gave a negative piece of him away, he becomes positive by a factor of 1. And because he just gained an extra electron, that made him negative by a factor of 1. So chlorine becomes negative, sodium becomes positive, and like two little magnets, they attract. And when they become positive, they're called a cation. Where's one of my cats? I should have him comment on this. Hey, Tigra, you want to comment on this? They're all asleep right now. Anyway, I'll pick one up later. Anyway, and the other one, if they've gained electrons, they become an anion. An means no or not, so they're not. So it doesn't make sense, not ion, but they are an ion. So, but anyway, they become negative. So that's anions are negative. So cations are positive, anions are negative, and because of this, they attract. But also because of this, they're easy to break apart, because if a larger atom flies by with a different charge, they'll break up and go with him. So it's kind of like dancing. Now, what I was saying about water earlier, this results in something known as a hydrogen bond because it is a polar covalent bond. So remember, water itself is covalently bonded, but when a bunch of water molecules get together, with one end being negative and the other end being positive, they click together like a whole bunch of little magnets. And this is what makes water so insanely important in biology, in life in general, in all of science. Honestly, if I could just teach like a mini master on how crazy important water is to like every freaking science, I would, because water is just that crazy. So, and we're going to be talking about water a lot in this class. So that's why water actually clicks together and forms crystals when it freezes. And because of these crystals and the way it's in such a structure, it floats. And you may be going, so what? My ice cubes float. Or so what? The icebergs that took down Titanic float. Well, there really isn't any other, except for a couple, molecules that can do this. Like, if you take a straight bar of iron and you walk over to, like, superheated vat of iron, like in a foundry or something, and you drop it in, and we have the ability to look through the vat of liquid iron, we would see that bar just go straight conk to the bottom. And that's true for everything that freezes, whether it be, something that's solid at room temperature, like iron, or not. Usually all of that, with the exception of water, just goes conk right to the bottom. And that's really important for, like, life, because, look at huge bodies of water like the ocean, or or ponds, or even the surface always freezes over. And granted, it can be really thick, but the bottom never does. And because that happens, all the fishies and the frogs live and go into hibernation at the bottom and then wake up and come up at the top during spring when the ice melts. Actually, there's a frog out in Arctic that actually is called the glass frog. He actually makes in his blood his own antifreeze, so he can freeze solid and still be alive. Isn't that insane? Yeah, no, don't inject antifreeze. That's bad. That kills us. That kills a lot of things. Don't do that. But I'm just saying, they make their own antifreeze in their blood, so when they freeze, their cells don't rupture, and they're cool. And then they unfreeze and go about their business. So that's why water is important. When it freezes, it floats. And that's extremely important to creatures living in bodies of water. And if you remember, life pretty much came out of our oceans. It would be bad if the oceans froze from the bottom up, because, yeah, nobody would have a good time there. Anyway, life would have not survived. So water is crazy important. That's why NASA is always looking for planets with water, because without water, you pretty much can't have life. Until some alien species proves us wrong on that end. But anyway, so again, he goes over the different types of chemical bonds. Now, keep in mind, this is a crash course with Hank. This is a chemistry one, so he goes into some details that you really don't need. But highly recommend if you want to watch. But just keep in mind, there's a couple of places where it's like, don't panic. But it's a good visual of how they come together. Like I said, videos and visuals, and the videos showing how things come together. Like, I wish I had an animation house to do this for me, but you don't. Now, depending on which molecules you put together, so now we're next step up, we get reactions. So atoms will swap out their bonds, like I said, in the ionic bonds, and very rarely the covalent bonds. They don't like to break down much, and if they do, usually something fun happens, like an explosion or stuff. Unless it's in a very controlled environment. So, there are basically 6 chemical reactions that happen naturally. However, 2 of them we don't really care about in anatomy and physiology, because well, one of them, interestingly, it does happen, but it doesn't really have much bearing, because it's happening to the blood as it comes out of our body. And, it isn't like we can grab the blood and put it back in. So we'll get that in a minute. But anyway, the main 4 that you really need to know before we go into how molecules come together and all that fun stuff is these. So the first one is synthesis. It's literally where you take one atom and another atom and slap them together, and then you get one that's together. So hydrogen, oxygen, slap them together, you get water. Bada bing! There you go. Decomposition is just synthesis in reverse. So we take one molecule or compound and we split it through a chemical reaction, and there, bada bing, bada boom, we have the 2 elements split out from each other. So for instance, sodium. So if I take the sodium and, or table salt in this case, so take the sodium and the chlorine and split them apart, you get sodium and chlorine hanging out apart. Now, this is where we get interesting. So, well, I like to liken it to like Foursquare dancing, or, just dancing in general. So, single replacement. So you have a couple here, nice compound, A, B, and they're dancing, and all of a sudden C comes in and goes, may I cut in? And then B gets left out, and A and C are dancing. So that's a single replacement, except with atoms. Keep in time, I'm talking about atoms, not actual dancing. Oh, it's like that. Anyway, double replacement is exactly like, you're doing like Foursquare dancing or country dancing or something like that. So you got 2 couples dancing, and all of a sudden they switch couples completely, and you get 2 new molecules, or compounds in this case, with that, because they've completely switched partners. So that's a double replacement. Double replacement we're going to talk about a lot. We hit on double replacement a lot. For instance, when a base and an acid get together, they go through a double replacement and always turn into salt water. And we get salt and water. And I'll show you that later. It's called neutralization. So you'll see this double replacement. Keep that in mind. It's coming back up later. Combustion is one of the 6. I just mentioned it because it's fun. Who doesn't like talking about explosions? So combustion is combustion. And then the 6th one they don't show here is, we don't really care about it, is oxidation reduction, which is rusting. So, you know, metal rusts because it's in contact with oxygen. Remember yesterday I said oxygen was known as the air that burns. And oxygen is really devastating to metals. It loves stripping electrons off of metals. So, yeah, that's why our blood is red, especially when it gets redder when it hits oxygen. So there you go. Fun facts. All right, next up. Again, she goes over, this is a really quickie one. I think I did this. But anyway, she goes over the main 4 that we actually care about, which is synthesis, decomposition, single replacement, double replacement. The other 2 we really don't care about in anatomy and physiology, unless you're planning to get rid of some bodies. I would suggest
Take a deep breath.
No. Gosh. All right. So there you go. So there's the first half of chapter 2. I'm going to take a break, eat some lunch, and I'm going to go ahead and do the second half in just a moment. So I'll see you in just a second. Bye.